Oh, okay, so I'll come over in the middle here. Okay, so now that we're recording, I just want to give everyone a little preview on what the class is going to be like, what my philosophy with teaching organic chemistry is, because there's lots of different approaches to organic chemistry, and maybe hopefully scare you guys to death. So, not that, yeah, but in a constructive way, I'm hoping. So, this class is going to be different than any class you've had previously because it's what I say all three kinds of hard. Some classes are hard because they're just an enormous amount of memorization. Some classes are hard because they have a lot of abstract concepts that you have to really spend some time wrapping your head around. And some classes are hard because they are just a lot of work. And this one's all of those things together. And the problem is that you're all pretty sharp. So, and this isn't pandering, it's true. The reason we have about a 35 to 40% DFW rate, DFW means students who don't get an A, B, or C in this class, isn't because people aren't smart enough to do this class. It's because the habits that smart people have leaned on because successfully for years often don't translate to this class. For instance, how many people here in Gen Chem said, or in physics, or went through, okay, well, here's the relationship, it's algebraic, I can rearrange it, substitute, solution, I have an A. How many people? You don't have to raise your hand if you're embarrassed by the fact that you can do that. That won't work in this class. How many people thought 100-level biology was easy because you could memorize all the stuff and spit it out on a test and do a little short essay? A bunch of people. Can't do that in this class. So this class is different because it has a lot of memorization, which is just the first part. It's like tools in your tool belt. Until you have the reactions, until you have the components of our rationale, you can't learn how to apply it. So the first thing is you need to know all of the reactions, you need to know all the mechanisms. And we won't get into the reactions and mechanisms until chapters 3, 4. So a lot of out the gate, that's the other thing. Out the gate, there's a lot of review, maybe a little elaboration, but it's going to feel very familiar. And so people go, I've got this. That's good that you've got it because you want your first exam to be, because it's the easiest exam in the OChem series, to be your best exam because you want that buffer going into these later exams. People who get A's in this class typically commit 2 to 3 hours a day, 5 to 6 days a week to this class. That's just reality. That's typical for an A. That doesn't mean you get an A, but it's typical of people who get A's. You can't do this class on 1 day a week or 2 days a week and get an A or a B. So you might be able to do it with a C on that, but that's pushing it. This class, and all chemistry classes and all good science classes, people feel comfortable with an understanding if they can discuss something. So if I'm discussing nucleophilic substitution, I can just have a conversation with somebody about it. That doesn't mean I can understand it. Understanding is being able to be presented with a problem and being able to apply your rationale to solve the problem. Being able to predict things correctly using rationale is understanding. And the difference between being conversational, so this is 0, this is conversational, this is problem-solving fluent. There's a huge talent gap in there. And we want to be on this side of the spectrum, not on this side of the spectrum. So it's really common after the second test or first test for people to come and talk to me and think, I thought I had this down. I really thought I knew this. That's because they were conversationally comfortable, but they weren't actual problem-solving comfortable. So I just want people to know where we're going with this. The tests are going to be predominantly multiple choice. Predominantly. But we've been working, but they're not canned multiple choice questions. We've been working on them for a couple of years now, and they're pretty good at getting to people's rationale, but there's no extra partial credit in a multiple choice, so you have to know it. The exception is most exams are going to have two other things in addition to the multiple choice. They're going to have a mechanism section, and the mechanisms are going to be free mechanisms. You're going to be asked to recite mechanisms. So how many people here have recited poetry as part of school at some point? Okay. That's more hands than typical. This is awesome. This is reaffirming the primary education system, because I've asked that question before and had like one hand go up. When you're memorizing poetry, you just kind of start at the beginning, work through it, get stuck, check in, start over the beginning, go further. That's mechanisms. Mechanisms seems really daunting at first, but the more mechanisms you run, and the more comfortable you get. And what I do is when I'm doing the mechanisms, I'll tell a story of what the rationale is for why I'm doing what I do as I draw the mechanism. So you have an auditory reinforcement, like you're explaining it to a third party. And you'll start to incorporate these fundamental patterns that you'll see in OChem, because what we want to get to in second semester, and here's the truth about second semester, there's so many reactions in second semester, very few people are going to be able to just stone cold memorize every single reaction. So you're going to have to start leaning on mechanistic insight to predict things. So first semester is setting a foundation. Second semester, hopefully, we're getting those foundations to click together and have a ability to predict and understand things that are put in front of us. Going back to everyone being super smart, or smart enough to pass OChem, which is pretty smart. Like I said, almost everybody in here can pass this class. It's just a matter of giving it enough time. Don't deprioritize it. If you take 2 weeks off of this class, you're not going to catch up. I know this because I failed OChem the first time I took it, because I took a couple weeks off. I was midterming and I thought OChem was under control, and I had a really good memorization skill set, and gosh darn it, I've always been able to cram everything in my entire life, and why was this class any different? And it turned out this class was a little different, and I couldn't catch up. Couldn't get back on top of it, so to make up for that, I had to go get a master's and a PhD. So anyone who fails this class, you have to go get a PhD in OChem afterwards. Sorry. Actually, my PhD is not in organic chemistry. It's in biochemistry, molecular biology with neuroscience. But it used a lot of organic chemistry. So I didn't like organic chemistry enough for a PhD in it, truthfully. It's fun, but it's not that fun. In the laboratory, academically, it's great. So I hope everyone's got time to do it. If you don't have time, or you have, if you think you might be overstretched, talk to me about it before we get too far into this. Like I said, we're going to start easy. The first chapter is chemistry review. Most of you have probably looked at the first chapter already and thought, okay, yeah, I know what a nucleus is, and an electron's kind of familiar, and ooh, orbitals. What's this molecular orbital theory thing again? What's an antibonding orbital? I thought that we could forget those after the end of 105. Oh yes, antibonding orbitals are back, and they're great. They're just high energy orbitals that rarely get occupied. Anyway, we'll get into that more. So, structure of the class. We have homework grade. It's worth 20%. It's mastering chemistry. Stay on top of it. Here's the deal. If people, this first assignment's going to be pretty brief. Get people into it. It's review. I'm not spending that much energy on it. I believe I have it assigned for 10 o'clock on Saturday, so that people aren't up until 1 in the morning on Sunday before an 8:30 class on Monday. If I see all of the activity happening on Saturday, meaning people aren't routinely working within the homework platform, I'm going to just start assigning homework 3 days a week, so that everyone has to be on the homework platform at least 3 times a week. And I don't want to use that method because that's a pain for me to have to set it up because I have to make extra assignment dates and it's awful. So I'm just going to assume that everyone's going to get into the homework platform and chip away at it. And the other thing about this is I have my homework problems that are graded, and then I open up the entire homework set, everything in the mastering system for you to practice. So there's lots of extra content for people to work with. In addition to doing mastering, which is a really good way to test how fluent you are with these topics, you should do note cards for every reaction. We're not going to encounter a lot of reactions in the first 2 chapters or 3 chapters, but when we start encountering reactions, note card them. I know it seems antiquated, but it works incredibly well. And there's 2 different approaches to a note card that you want to use. A lot of people only do one of the 2. Let's say you have some reaction where reagents A plus B treated under conditions X produce C. You want to make 2 note cards for this. The first is on one side of the note card, you do that, and then on the other side, you flip it over, and you have the answer. The other one is what are the reaction conditions that drive this reaction? Flip the note card over, reaction conditions X. These are 2 different separate processes, and if you're only comfortable with an outcome under a condition, a lot of the time you won't be able to come up with a condition that comes with the reaction. And this one in particular is very important because when we start to do synthetic mechanisms or synthetic pathways that have 2, 3, 4 steps in them, we're going to be leaning very strongly on what kind of reaction conditions give us outcomes that we need. So 2 sets of note cards, and just flip through them daily. Drill them so it's there, and then you just retouch them every day or every 2 days. Break out a chunk of them. You don't have to run them all. Zip through. If you got them all, great. Put them back in. If you don't, you drill them a few more times, refresh them, and we're set. So this really important tool, practicing mechanisms freehand, very important tool. Other things that are incredibly important for student success, not doing this solo. Occasionally, we have super students who just do this class on their own, but it's rare. One of the best tools we have is study groups. And this is another thing that people have historically been successful without using. Like, I don't like study groups. I'm a Lone Ranger. I don't need anyone's help with these classes. But this one, the folks who work in study groups productively together typically get A's and B's. The ones who don't occasionally get A's and B's too, but it's less frequent. Our grade distributions are definitely improved by people who do voluntary study groups. So if you know somebody in this class or 2 somebodies and you can line up some times where you can sit down and work on problems together and troubleshoot things together, that makes a big difference. Another tool that is not set in stone yet, but hopefully will be by the end of the week, is the Vice Provost for Student Success has identified some funding to get some peer mentors inserted into a couple classes, and OChem 1 happens to be one of those classes. So hopefully by the next couple of weeks we'll identify some students who are very good at this class in the last few years who will be able to do study sessions a couple times a week. So hopefully we'll have, I'm hoping for 4 study sessions, 1.5-hour blocks over the week. And that's going to be stuff that has to fit into their schedule also, so they're going to be all over the place. I hope they align with most people's opportunities to see that or participate with it. I would encourage people to do that as well. One of the incentives I'm going to do to try to get people in there is I will be embedding an occasional test question into the things that get discussed at these groups. Now don't fret if you can't make them at all because of being committed to other things. I'm going to post the problem sets that get run on Blackboard as well, so you have access to them if you want to run them independently. But so everyone has access to those same working sheets. But that's not set in stone 100% yet. We're really hoping it will be by the end of the week, though. It kind of came together when all of a sudden the state gave us some money to do college with. So let's see here. Other than that, 20% is homework, 3 tests at 20% apiece. Finals also worth 20%. Finals cumulative. Final will be the ACS final. That's American Chemical Society final. It is all multiple choice. It's nationally standardized. It's our students typically score. Our average score is nationally average. That's good. So one of the things to keep in mind is for $10, you can buy a study guide for the ACS organic chemistry test from their website. You can split that with friends and photocopy it. I said that on tape. Hopefully I don't get in trouble for that. Anyway, use it. The ACS study guides are actually pretty good at coaching you through the specific topics that will be on the test and give you a little bit of insight into how they do it. Not to scare everybody, the ACS final happens to be, the ACS organic chemistry final happens to be notoriously difficult even for ACS finals. I will curve it. Ooh, curving. Everyone wants to know about curving, right? Because it's organic chemistry. I don't curve individual tests. I reserve the opportunity to curve until the very end of the semester when everything is compiled and I can see the whole picture. I give people an update on what the class average is so they know where their standing is next to other people in the group. But I don't curve individual tests. Organic chemistry, let's see, have I ever not curved it though? I've always had to curve organic chemistry a little bit. I've never curved more than 12%. So, but it's been a while, so we'll see. Maybe I've gotten soft. So when the first test happens, I'm sure everyone will do well because it's not all review, but it's predominantly review. That's not true. Everyone, sorry, I don't want to set a false narrative. The first test rarely goes as well as it should. So I'm not going to tell horror stories because I don't want to scare anybody, but it should be the best test, but often it's not because people are overconfident with the content. So just be ready for it. I think you guys will be fine. Let's see here. So any questions before we, well, actually I should go through this list. Oh, okay. One last thing. Attendance and note-taking. A lot of people are used to PowerPoints. I don't do PowerPoints. I chalk talk everything. I do PowerPoints for biochem because there's so much visual content I can't draw. Me drawing the tertiary structure of a protein that's folding is horrific and not helpful at all. So I've recently switched over to PowerPoint for biochemistry. But for Gen Chem and OChem, I just do it on the board. And that's for two reasons. One, because it's more engaging for me. I hate talking off of slides. Two, it keeps me pacing things appropriately because if I have time to write it, turn around and talk about it, everyone else has time to write it and listen to it. And it makes me cognizant of how much content I'm delivering in an hour and 15 minutes because I'm a real jerk with PowerPoint slides. I'm like, oh my goodness, I'm behind. Oh man, hold on. Everyone's seen that. And read it. It's all posted on Blackboard. Have fun. And everyone's like, oh geez, okay, I'm out. When I posted resources before, like slides, attendance went way down. And other people come into my lectures occasionally and go, wow, you got a lot of students for Chem 105 in here. How do you do that? Well, I just don't give them anything online. They have to come to class. It's true. It's true. So, because I chalk talk, you should be here. Now, I'm ruining that by making videos that are going to be for the online people, but you guys know that you don't really watch videos when you watch videos. You like hit double speed, make me talk like a chipmunk, just kind of like have a coffee. People have admitted this to me after I didn't even know fast forwarding videos was a thing, but I didn't have the internet when I went to college. So, so I'm behind on the curve on that. I think that's everything now. Any questions before we get started on chemistry review? Don't be shy. Somebody's got a question. Nobody's found an inconsistency in my syllabus yet? You haven't looked? Oh. Bold move, being truthful. Slacker. That's good. Most people haven't. Most people don't. I recommend reading the syllabus. Yes.
Are you going to post the mastering code for the class? Did you see it anywhere?
Has anybody else been able to log in to mastering yet? We have a few people. Do you get a mastering code? You should get a mastering code when you buy it, and it should be linked to the class, correct?
Yeah. If you access it via the course shell on Blackboard.
On Blackboard. Yeah. That. Thank you. Yes. So when accessing mastering, you have to do so through the Blackboard shell. Yeah. And if you encounter a mastering technical glitch, I literally cannot help you because I have no control over that system. So you have to work with their folks. They're very helpful typically. And I like mastering because of all the online platforms we've used. It seems to be the least awful. So, give me a heart attack with that question. I was like, did I not miss something? Yeah.
One of the things that says in the syllabus is you have a 3-day window to take each exam.
Oh, geez, did I not erase that? Okay, that's for the online class.
Oh, okay.
Yeah, no. There's no 3-day window. Oh.
I mean, I was going to just roll with it.
I know, like, sweet. No, this is because the exam takes 3 days. No. I will amend that. If I haven't amended that and posted the correction, harass me relentlessly until I do. That, I thought I took that out. Maybe I man, I hope the online group doesn't have the face-to-face syllabus posted. I'm going to find out. Let me make a note of that.
Other differences in the syllabi?
Mostly testing. Yeah, the tests are in the same week too. So the testing window is the same week that you guys take the test face-to-face. Okay. And I'm hoping that you'll meet some of the online folks and they'll meet you at these student-led tutoring sessions so that we can network the online group. Because as difficult as chem is face-to-face, it's way harder online. So I'm hoping if we can get you guys networked, we can get more people to be successful with the online OChem. Yes?
Just to confirm, you will be posting your videos on our access as well?
I have a YouTube page I'm going to be dumping them onto because I like to own the videos I produce instead of the university owning them. So, assuming this works, then yes. Yeah, then I'll make it available. So if you're sick for a day, that would be a good backup option. But the first file already got corrupted, then I had to reset it. So that hadn't happened yet. I've been doing videos on this for online classes for a couple semesters now, and I had never had that happen until this morning. But you never know. So, but I'll try to. Any other questions? Oh,
You were wondering if you might have posted the online syllabus. I mean, they didn't have it has like a class time in here, but it also then has its finals because we have to sign up for the student registrar for exam testing. Oh, you do?
I'm going to have to review this. Yeah, I'm going to have to go back through the syllabi.
Okay.
I was making a lot of syllabi at the last minute, and I had a feeling. And to be fair, I've never once produced a syllabi that didn't have some conflict in it, because you take a syllabus and you roll it forward and you start changing dates, and you're like, what am I going to do this semester that's different and fun? And then lack of hilarity ensues. And every semester somebody points out some kind of conflict. So it looks like I am still batting 0 for perfect syllabi. So I need to work on that. Yeah.
This is kind of a textbook question.
Oh, yeah.
The e-text that we get with mastering, if we choose to purchase that, is that an equivalent to the textbook that you have listed, or do we need it?
It's exactly the same textbook, but it's just digital.
Okay.
You have to access it through Blackboard, though.
Okay.
Unless you screenshot every single page. Which, if you have shoddy internet, I would recommend doing. Or some people just find that PDFs of old versions of textbooks just happen to be online. And if you bought it, the reason is because I have had people who, because of financial constraints, don't have good internet at their home, and they can't. You have to have the ability to upload it every single time. It doesn't store. It might store to devices that are like a phone, though. They keep changing how much access you have to it, but the e-text is exactly the same thing, except that it has links embedded in the problems to the specific points on the homework, so you can actually pull up sections of the book directly from the homework platform.
Okay.
You don't have to get the paper book if you're okay with e-text. I can't read an e-text to save my life, because as soon as I'm moving the screen instead of my eye, I know it's because I'm old. 10 years ago, students hated e-texts. They didn't want them. And now students are more comfortable with e-texts based on the price point. I don't know if anyone really wants them, per se. I like textbooks because they're comfortable. So that's also a good question. Yes. Oh, we'll go here. It's okay.
Okay.
We'll go here.
How much does mastering cost?
I don't remember exactly. Is it 70 or 80?
It's 70 for without the e-text, 120 with the e-text.
120 with the e-text. And that's for the 2-semester series. That's a 24-month access or 12-month access.
I think it's
It's for the semester. What's the 2-semester cost?
Have that as an option.
Yeah.
You can rent it on Amazon for
At-
$33 too.
Yeah.
Yeah, it's the book plus so you can get the e-text plus the mastering for 120, which is you need to have the mastering regardless. So it's really $50 for the book access. But like I said, if you want to get the earlier edition used, this is 8th. You can get 7th edition. It'll be fine. Organic chemistry did not change significantly in the last 3 years. At least organic chemistry for like intro level organic chemistry, like learning to walk organic chemistry hasn't changed at all. So, oh, sorry, we had the hand up here first. Models are optional, 100% optional. You can use them in exams. Some people find them incredibly helpful. Some people don't need them whatsoever. And geometric three-dimensional visualization is one of the 6 discrete intelligences. Just because some people can visualize something, turn it in their head, and know exactly what's going on. Some people really, really, really struggle with that, and models help them visualize what's going on and taking something and moving it around. You'll see me miming in front of you like I'm holding something, like I'm in Star Trek. I'm like spinning something and flipping it and blowing it up. I'm seeing what I'm doing. You guys just see me moving my hands. But some people are really good at seeing things in their head, and some people are not as good. You get better with it with practice, though. So I'd recommend, as you use a model, try to practice it as well. But you do have access to the model during class and tests if you need it. So if you want one, as soon as possible. We had a question back here.
Is this the textbook used for both semesters?
It will be. Yeah, we don't change textbooks on classes midstream unless you take more than 2 semesters to get through it. But I don't see this book getting changed. Neither myself nor Dr. Tomko have any issues with this book right now. So, yes.
You reference virtual office hours in your syllabus.
Son of a gun, I totally put the wrong syllabus on there. That is the wrong syllabus. There will be no virtual office hours. My office hours are immediately after this class. Wait, is it?
That's listed as well. Yeah.
Oh, it is? Okay, there's no virtual office hours. I have to get rid of that too. Oh, goodness. For the people who are online, who don't necessarily have access because they're not here to me in person, I can set up a call with them occasionally. I've tried to do that historically using some software where I can draw and they can see what I'm drawing and vice versa. The problem is that participation was so ridiculously low, I couldn't get people to participate in it. So I'm moving to an on-appointment basis for people who are online, you guys. Okay. So, but y'all are here. I'm usually available after class, usually, to have a discussion if you need, or I'm going to have office hours as the actual in-person office hours. All the time. Yeah.
So does that mean that sending me questions by email is acceptable, or is that still?
My turnaround time on those questions are going to be very, 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 very slow. I have 260 students this semester between my 4 classes, and I'm just not going to be able to do a lot of individual work outside of the office hours addressing people's questions. I have pockets of time where I can get into those things and try to sort through them, but if it's a discrete technical question on a single problem, I'm not going to be able to promise a really rapid turnaround on that kind of stuff. So that's just to be honest. If there's a structural question with the class or a major logistics issue or a serious concern, I'm going to prioritize those things. And it's remarkable with over 250,000 students, how many of those things pop up over the course of every single week. So I'm going to be prioritizing that kind of thing over actual individual questions. It's worth a shot though, but it's not personal if I don't get back in the next 48 hours on it. And almost always by the time I get back to people, they're like, oh yeah, I solved it. I figured it out. It's resolved. So I sat there and I did the whole thing and they're like, really? So, well, it's called, so this class, like some other classes, I'm sure some of you have taken, I had a professor who called it taking time to wrap your head around something. It's remarkable what letting things just kind of spin for a little bit can do for problem solving, and if people are working on something collectively, the group can solve things with a little bit of just wrapping your head around it. Very, very often people just need to just invest a little more time before they reach the conclusion they can't do it. It's remarkable what a little time does sometimes. Most of the time. These are good questions. Any other questions? However, if you have questions, you can ask them in class. Because it turns out, when I was developing online curriculum, I can lecture through the content of class in under half the time allocated for contact hours. But every time I teach a class face-to-face, I'm always pressed to get everything in. And the reason is, it turns out I'm spending over half the time of a class experience just answering questions, and people will say, hold up. It's not uncommon for me to do something and to see panic across the room, which means I need to do some extra examples. And usually the panic level subsides as I do more examples. But this is everyone's opportunity. I mean, that's the main reason online classes are harder than face-to-face classes, because you guys have the ability to real time get things addressed mid-lecture and have questions in lecture, and they'll benefit from those questions, but can't ask them real time. So about half the time of classes usually involve doing that kind of thing. Other questions? When is the class on? 9:45? 9:45? Okay, we're doing good. We can do Gen Chem review, and no, we don't have to do it that fast. So there's a holiday next week that I also didn't have on the syllabus, I think. Okay, good thing we can go fast through review. It's just review. It's just molecular orbital theory and hybridization. It's not bad. So any other questions before you? Yes?
Actually, I'm sorry, I was listening to this, but Master in Chemistry is currently down for registration.
Probably just because so many
And
people are
Pearson
using
knows
it
about
and
it. They said they know that if you go into the Pearson website and log in, they say that they're aware. So I don't know how long they're going to take.
It's usually resolved very quickly. It's probably Monday. It's probably the first day of classes for most of the nation. And everyone's like, oh, I haven't logged in yet. Oh, no. So they're probably bogged, but keep bogging them down. Just give it to them. Let them, yeah. Just spam them with the try, refresh, and just, don't do that. Give them 30 minutes and try again. Okay. Also, you'll adapt to my sense of humor. It's sarcastic and snarky, and some people tell me that in my student reviews. But, we have to make this fun somehow. So, at least for me. I hope you guys have fun too, because I love organic chemistry. It's my favorite academic topic in chemistry. All right, let's get started. Yeah. Better color. Okay, so organic chemistry, there was as a field, it's relatively new, because there was a widely held assumption or belief structure that things of biological origin could not be made synthetically from things that were not of biological origin, until there was an experiment which had ammonium cyanate and it was heated and produced urea. So this was an inorganic salt, and this is an organic biological product. Now, I'm going to have spitball and ask people, what's organic chemistry? What is the organic chemistry the study of? It contains carbon. This contains carbon. But you're not really wrong. You're not wrong. I know, the book said it was. All right, so, and that's generally how people view it. It's a specialization in chemistry that focuses on carbon and how carbon bonds to itself and how carbon bonds to other things, often in large polymeric structures. So if we start with simple discrete things, but then as we grow, let's see, what has carbon in it? DNA has carbon in it, large biological polymer. Proteins, large biological polymers. Carbohydrates can be discrete or large biological polymers like cellulose. Lipids, not polymers, but fairly large biological molecules. So we just covered all four categories of biomolecules are carbon-based. So, organic chemistry is a nice lead into biochemistry as well. Also, let's see here, pretty much all synthetics. So all plastics, synthetic fibers, pretty much everything in this room a product of some kind of organic chemistry process. So it's a really huge field, actually. So even though we're just focusing on carbon, the diversity of the chemistries that we can do as part of organic chemistry is remarkably diverse. And it's all based off of carbon having a preference for bonds. So we're going to get into this in a little bit more detail with bonds and lone pairs or cationic structures, but carbon is happiest when it has 4 bonds and it's right? I'll just write that down. Now, you're like, Dr. McGill, you just said that carbon's happy. Yeah. What we're going to deal with a lot here is non-numeric predictive questions associated with different carbon compounds. And what you're going to develop over the course of the next 2 semesters is an intuition for what structures are happy and what structures are not happy. We want things to be happy because happy means stable or / less reactive or non-reactive. It's one of the lingos you'll hear a lot coming from organic chemists. You're thinking, that's a silly rationale, but you'll get used to it. In the same way that your ear, when you learn a language as a native speaker, why did you say something this way? Well, because it sounds right. That's kind of where we want to get to with the organic chemistry, but we want you also to have the rationale-based approach, but you also should be developing intuition as we go throughout the semester for what is happy and not happy. And this is carbon at its happiest. So, oh my goodness, the basics of review. Okay, what's an electron?
Negatively charged particle that orbits an atom.
I'll give you a pass on the orbiting thing because it sounds planetary. How much mass does it have? Negligible for all intents and purposes. Cool, we don't have to know it exactly because it's not physical chemistry. Sorry, physical chemists may be present, or somebody who likes physical chemistry. Physical organic chemistry is pretty great, though. Protons. Atomic mass of 1. Neutron.
Mass of 1, no charge.
Mass of 1, no charge. Awesome. You guys remember something. This is great. What's the atomic number determined by?
Number of protons plus neutrons.
This is amazing. Wait. Number of protons. Atomic number.
Oh.
Atomic mass is protons, neutrons, and it's the running average of all the natural current isotopes. Okay, so an atom's identity is determined by what?
Number of protons.
Protons. And there's variations on that identity based on number of neutrons, which are called... All right, you guys just killed it. That's awesome. 1 page down. I didn't even have to draw anything. This is fabulous. Ooh, here we go. Okay, so it's remarkable how much we lean on quantum mechanics as part of our explanatory power in organic chemistry. And remember that quantum mechanics is the notion that we can't simultaneously identify the momentum of an electron and its position. So we have to make spatial predictions based on the probability where they are likely to be at any given energy level. And these are orbitals. And so even though we call them orbitals because originally people thought of the electron as this thing that was physically orbiting, we now know that's not the case because that's absolutely particulate in nature, and electrons have a dual nature of both particulate and wave. So, basics of orbitals. Let's see here. each orbital or suborbital can hold a pair of electrons. They have to have opposite spins. And so the first orbital is always an s orbital. Let's see if I can see this on the screen at all. Oh man, that is utterly invisible. I'll see if I can. This may not work out after all. So s orbitals spatially in 3 dimensions. We've got, let's see, our x, y, and z axes, and they're spherical. Second orbital, so we can have a pair of electrons in there, so 2 electrons. Second orbital is p orbital. How many subshells are there in the p orbital? 3, x, y, and z axes. So we have 3 suborbitals within the p orbital. Each of those suborbitals can hold a pair of electrons, one positively, one negatively spin. So we can have a total of 6 electron in there. And if we're drawing those in, now we have something that looks like this. Now, what I want everyone to get a sense for here is that intuitively we have these nodes in the center and along planes that prevent or have a very low incidence of electrons penetrating into these zones. However, in terms of electrons not occupying the same space, this is a fairly efficient way for having a density of electrons here that are then surrounded as we move away from the nucleus. So as we get more complex with our orbital structures, we're basically just defining ways to put electrons in space most efficiently without them being in each other's zone. They're kind of like 3-year-olds. They like each other, okay, but if you get too close, they start to get pushy. So I have a 3-year-old. Never used that analogy before, but it's remarkably similar. A 3-year-old with a toy, actually. So what am I doing here? Third are d orbitals. There's a variety of those. There's actually 5 of them. So we have 5 suborbitals there. So a total of 10 electrons. And last we have F. And there's 7 options there with 14 electrons. Now, we are going to spend a vast majority of our time in this land of S and P orbitals for organic chemistry. Every now and then we'll branch into a little bit of D orbital, but as soon as you get into F's, you're really doing bioinorganic chemistry. Or, that's pretty much where you're at, or just inorganic chemistry. So we're going to be focusing a lot of this. So let's zoom back out a little bit, because let's look at carbon. I totally forgot to bring up, do we have a periodic table? We do not. I'm going to have to get a periodic table for this class. So who's got periodic table in front of them handy? Ah, excellent. We have one handy. So how many valence electrons are in carbon? We've got 4, right? So how many electrons are in carbon? 6, right. What's the difference between a valence and non-valence electron?
Valence are in the outer shell.
Valence are in the outer shell. What's that mean, though?
They're the ones that can form bonds.
They're available for bonding. Ah, okay. So if we've got carbon, which has 6 protons, and when neutral has 6 electrons, the first 2 electrons go into which orbital? The 1s orbital. So 1s orbital gets 2 electrons. It now has a duet, which means it's happy, or it has the equivalency of an octet. Whenever we have full orbitals for each primary energy level, things are very, very, very less reactive than they are when they're approaching a full duet or full octet. So now this is at the core. It's buried inside the milieu of electrons, and it's not really accessible to other electrons. So if you're thinking about accessibility, it's not just energy level and the fact that these are happy. If this is the 1s orbital, and this is the 2s orbital, and this is the 2p orbital, and bonding takes place by virtue of sharing electrons or transfer of electrons. If you're looking to share electrons, it's much easier to share an electron here than access all the way to the core and share an electron here that's also less accessible and vastly more stable than here. So a lot of this is explainable through just accessibility of outer electrons from inner electrons. So now we got through the 1s, we've got 4 electrons left. We've got 2s and 2p orbitals. 1 electron here. Fill the 2s first. We have 2 electrons left. And they go sequentially in there, leaving one of these suborbitals vacant for now. You'll note that every book has its problems. The book uses this double-sided arrow here. And Dr. Bruce is a very smart person. I'm sure there's a reason for it. I don't know what the reason is. Because in organic chemistry, a single-sided arrow like this means 1 electron, and a double-sided arrow means 2 electrons. When we're doing mechanisms, if I'm moving a pair of electrons, like I have let's do something. General nucleophile, a pair of electrons, and they attack something with a double-sided arrow, that means both electrons are going. If I have a radical reaction, like I have a carbon radical, single-sided arrow means 1 electron's going. These nomenclatures matter. They matter enormously, and why this book uses a double-sided arrow to denote single electrons, it gives me the willies. So, just by virtue of consistency. So I'm going to be denoting every arrow as a single-sided arrow if it's 1 electron moving forward. If you throw out in a mechanism a double-sided arrow for a radical, that's not going to be correct. If you throw out a single-sided arrow for a pair of electrons moving, that will also not be correct. Will it mean that you get 0 credit? No, unless that's a multiple choice question and there was a correct answer available to you. But it's worth something. So just be cognizant of what kind of arrows you're drawing. Okay, so let's take a look at some of the basics of what happens with species that are non-neutral and what drives them to be non-neutral. So, basics of covalent bonds. We typically want to see 8 electrons in an outer shell, unless it is hydrogen or helium, and then we're going to see a pair of electrons in the outermost shell because they have nothing except for an s orbital available to them. So let's see here, rationale-wise. Sodium can easily lose an electron to become positively charged. Likewise, chlorine can easily gain an electron to become negatively charged. What's the rationale for this? Simple loss of an electron or gaining of an electron, in the most basic sense.
Stabilization.
Because typically housing charge isn't something that in a vacuum is something that atoms do, right? Why would you go from a neutral species to a charged species?
It satisfies the octet.
octet, right? Because in the case of sodium, it's all the way over on the left side of the periodic table. By virtue of losing its one extra electron, it moves back to the preceding octet on the far side of the right side of the periodic table. In the case of chlorine, it is a halogen. It's one away from an octet, so if it gains that electron, it actually becomes pretty happy holding on to that charge, which is why we have something here that's very electronegative and something here that is very not electronegative. This species actually prefers to be charged versus carrying charge. So this is the rationale for ionic bonding, right? Because if this happens and sodium wants to give up an electron and chlorine wants to gain an electron, this can happen in concert. That electron can move from the sodium to the chlorine. Both become charged, and they have an electrostatic attraction, and that's an ionic bond. What's a covalent bond? Sharing of electrons, right? So we're going to be seeking the ability to get octets through sharing of electrons. Let's start with just really simple versions. Chlorine plus chlorine. Both of these have 7 electrons in their outer shells. We can share 1 electron apiece. Hopefully everyone remembers that a single line denotes a bond. That bond contains 2 electrons. Now that we're sharing these 2 electrons through space between these nuclei, we have a bond. That gives us 1, 2, 3, 4, 5, 6, 7, 8 electrons on this chlorine, and 1, 2, 3, 4, 5, 6, 7, 8 electrons on this chlorine. Both now have an octet. Both are happy, and we have chlorine gas. We can do the same thing with water. Let's see here. We've got oxygen drawn with its 6 valence electrons. We have 2 hydrogens. Let's see here. I have to throw some more. I'm going to just be this. Anyone ever have a foreign language class that's semi-immersion where this teacher comes in and just starts speaking to you in a language you don't speak? Yeah. There's a little bit of that that's going to be happening. You'll get comfortable with it. It's not quite as abrupt, though. I will very commonly refer to hydrogen when it's positively charged as a proton. Some people haven't heard that before in Gen Chem. The reason I refer to it as a proton is because hydrogen has a proton. How many neutrons does hydrogen have? 0. Not fooling any of you. It typically has 1 electron. When it loses its electron, because it's good at losing electrons, what's left? Just a proton. So a hydrogen carrying a positive charge is literally a proton. So as part of mechanisms, it's really common for, I'm moving off screen. I'm going to have to get used to this. For some nucleophile to attack some species, grabbing a proton, which gives up its bonding electrons and moves them to the chlorine, and then you have something that looks like, I'll just go with that to make it easier. Something like that. My rationale, I would say, nucleophile has extra electrons. It's looking for a home for the electrons, reaches out, grabs a proton. It overextends the number of bonds on the proton, breaks this bond, pushes electrons to the chlorine. Voila, we have a reaction. Don't worry, this will be super, super simple by the end of the semester, but you don't have to know it right now. But I'm going to be using the word proton around hydrogen a lot. So don't worry about it. So here we have the opportunity for oxygen, which has 6 electrons, hydrogen, which has 1 electron apiece, to share here and here. giving us 2 bonds to water with 2 lone pairs. Notice here we have 1 bond and 1 lone pair. Here we have 2 bonds and 2 lone pairs. Let's see, what's another good example? Ammonia. Nitrogen has 5 valence electrons. We'll have 3 protons. We can share here, here, and here, giving us ammonia, which has 3 bonds and no one corrected me.
I was raising my hand. I was like, where did you get 1 lone pair?
So here's a rule, guys. I screw up all the time because this is real life. When you see things out here, you can see the whole picture. You track the whole thing visually really easy. When you stand up next to the board, you see like this much. So as you do a reaction, it's really easy to forget where you are. I mean, and I know that I'm pretty used to doing this, but you still make mistakes occasionally. And when you get it's like that game of telephone where somebody talks to somebody relays that message. It's amazing how far you get off track. If I screw up, you're like, dude, Dr. McGill just screwed up. My back's turned, like, I think you screwed up. Just let me know. Just make sure I'm wrong first. Because if I start to second guess myself and I was right the whole time, it's really bad. But I have been like across the board still doing something wrong. When I realize I'm wrong, I turn around, I was like, how long have you guys known that I've been doing this wrong? And like everyone's like, yeah, we know. I'm like, great, thank you. Thanks for letting me know. 1 bond, 3 lone pairs, 3 bonds, 1 lone pair. And then we have, we're going to do carbon. I'm not going to draw it out, but it has the ability to form the 4 bonds with no lone pairs to make methane. So, if we were to take the time to do the formal charges for these, who here remembers how to do formal charges? Who here? Oh, okay, we should probably talk about formal charges then. We'll take the time to do formal charges. You'll notice that formal charges, when this becomes methane, formal charge is 0, 0, 0, 0. Formal charges of 0 mean things are stable, more happy than when they're carrying charge. 0, 0, 0, 0, 0, 0, 0, 0, 0. You see a trend, I think. You're going to get good at shortcuts in OChem. When carbon has 4 bonds and no lone pairs, its formal charge is 0. Always. When nitrogen has 3 bonds and 1 lone pair, formal charge is 0. If I add a proton to it and make ammonia, now it's a formal charge of +1, which is why the ion has a formal charge of +1. So this is its happiest state. Oh, jeez. Terrible green. Oxygen, 2 bonds, 2 lone pairs is its happiest state. Halogens, 1 bond, 3 lone pairs, happiest state. Any divergence from that, you're going to be looking at a positive or negative charge, and you're going to be looking at formal charges. So you don't have to go and calculate every formal charge from scratch when you see these patterns.
Professor,
Yes.
question over here.
Yes.
Wouldn't there be a charge to the overheat structure? Or a slight one? In the case of,
That's not a charge. That's polarity of the bond. Yeah, so full charges, as denoted by formal charges, are possession of electrons, not partial possession of electrons. So and in the case of methane, the answer would be no, because there'd be no net charge. So there's polarity to these bonds, but there's not actual formal charge.
Formal charge in reference to a specific atom or the molecule as a whole?
Yes.
Okay.
So let me explain. No, that's exactly. So if we were to do, let's do hydronium. So hydronium. So you put acid into an aqueous solution. So we've added some acid to some water. You guys have probably seen something like this in Gen Chem. Depending on the book you used, it may have been shown as this. So protons do not exist predominantly as free protons in aqueous solution. They very rapidly bond to water, forming hydronium, which acts like a free proton. So what this looks like is we've got water, and we've got our free proton, and there's much more water in aqueous solution than there are free protons, so there's an abundance of this substrate to take place, and we have this lone pair of electrons reaches out and contributes a pair of bonding electrons to the proton, and that consumes one of our lone pairs and puts a net positive charge on the oxygen. So this is hydronium. So this is a really good opportunity to look at lone formal charge per atom and then formal charge per molecule. So if we're doing the formal charge analysis on just the water, formal charge is, oh good, I didn't write it down. I'll fake it. So formal charge is an oversimplification of possession of electrons. What it tells you is how many electrons the atom is actually possessing as part of bonding or part of having in lone pairs. And the equation is, I believe, the number of electrons in lone pairs or non-bonding electrons. In this case, we'd have 4 of them, plus 1/2 of the number of electrons in bonds. And because this just neglects the difference in polarity of a bond, we're just going to say if you're sharing a pair of electrons in a bond, half of the electrons go one way and half go the other way. It's just a simplification. So for oxygen, just redraw that. Oh, and this is, there's another part to this. What's the rest of the equation? What's the other variable? The number of valence electrons. So it's the difference between the number of valence electrons and the number of electrons it possesses. So how many valence electrons in oxygen? 6 electrons. How many electrons does it possess solely that are non-bonding? 4, because it's got the 2 lone pairs. And then it's got 2 bonds. Those 2 bonds contain 4 electrons. Half of that is 2. 0. So here, oxygen has formal charge of 0. The proton, super easy. Proton has 1 electron. It has no electrons that it's in sole possession of, and it has 1/2 of 2 bonding electrons, so it's 1 minus 1, 0. So both of those have 0. So the net for the molecule is 0, which we should see because if it has a positive or negative charge, that should match the formal charge for the entire molecule. So in this case, hydronium, we have a positive charge on the molecule of +1. So one of these, the sum of all of these should be +1. Hydrogen, 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 1 bond each, none of these changed, so they're all still 0. Oxygen is where the difference is. So we've still got 6 electrons in the valence shell. It now only possesses 2 electrons that are non-bonding, and then you get 1/2 of the number of bonding electrons, which is 6. So that's 3. So 6 minus 2 minus 3 is +1. So the oxygen carries a formal charge of +1, and the molecule carries a charge of +1 as well. Yes?
I apologize if you explained, but in the equation, should the 1/2 of the electron bonds be subtracted?
Yeah. Well, no, because I had a valence minus the product of these two things. So, yeah. I'm trying to remember the picture of it in the book. It's displayed lots of different ways. You can go valence minus all of the electrons, like this, or you can just go valence minus bonding minus, just do it sequentially. Yeah. Yes?
I think the book points out, but you can actually just, rather than doing half times the number of electrons in the bonds, just count the number of bonds. It's just a little easier.
You can do that too. And I guess I'd do the shortcut where I just count the bonds thinking 1 electron per bond. So, yes?
For the hydronium, isn't the number of valence electrons for the oxygen 8?
Nope.
So much.
Nope, because it's number of valence electrons in its normal atomic state, and what we're looking at is the amount of formal charge based on the electrons that it's in possession of as part of this bonding scenario. Because otherwise, if we were adding electrons in every time, we would just be, wait a second, 8 electrons.
There's 2 from each bond and then 1 there.
Let's do a Lewis dot structure from scratch. So if we're doing a Lewis dot structure from scratch, and we want to do Lewis dot for hydronium, we're going to have to put oxygen at the center because it is our most electronegative. We're going to have to put our 3 hydrogens around it. How many electrons total do we have in the valence for this oxygen and the 3 protons total? We have 9 electrons available based on their atomic structure. So we've got 6 here and then 3 from the 3 protons. We've got 9 electrons total available to us. We have to use up our first 6 electrons in bonds. So 2, 4, 6 electrons right there. So minus 6 electrons in bonds. And then we've got 3 electrons to play with. I just totally messed this up. Thank you.
Yeah.
Thank you. 9, charge of -1, going fast, 8 electrons, -6, gives us 2 electrons left, gives us our lone pair.
So in the equation, it's the number of valence electrons of that atom at base. Or
Yes, because once we start to get into the actual compound, you'll see that we're not dealing with atomic shells very often. When we get into hybrid orbitals, it's all going to be, we're going off the thing there. And we are out of time, so I will be seeing all you guys Wednesday. We'll pick it up from there, and hopefully we'll make good headway.
Couple minutes.